All right, it seems that no additional people are joining, so I will start. So this is the summary that I used yesterday. I will go through very briefly. So we went through what is combustion, why do we use combustion. Then we spent some time describing some fundamentals of chemical kinetics and modeling. We presented the global fuel properties, and finally the composition of fuel and their potential impact on reactivity and also formation of pollutants. And today we will concentrate on the experimental techniques which are used for assessing chemical kinetic models. A chemical kinetic reaction mechanism that I showed briefly yesterday, they can be either handwritten or automatically generated, but they rely on experimental data obtained over a large range of conditions. I should say as large as possible. However, combustion is a complex, generally exothermic phenomenon involving strongly coupled chemical processes and physical processes. Thus, in order to better assess chemical kinetic reaction mechanism, it is preferable to design experiments where the complexity of physical processes is minimized and concentrate on the observation of chemical phenomena. This is the case for ideal reactors, such as plug flow reactors, perfectly stirred reactors, shock tubes. In practice, the experiments should be performed under condition where ideal reactor models can be used, which means operating a GSR under highly diluted conditions or under near hydrothermal conditions. Such kinetic reaction mechanisms need to be validated through extensive comparison of modeling prediction and experimental results obtained under well-defined conditions. A wide range of experimental facilities can provide such data, which are usually described as global or detailed. So if you remember yesterday, I presented the global data that can be used, such as ignition delays and flame speed, and detailed data consisting of concentration profiles of a variety of species, from the reactants to the final products and intermediates, which can be stable intermediates or unstable intermediates, such as radicals and atoms. By combining data obtained from several techniques and operated under different conditions, one can check their consistency and use them to constrain chemical kinetic reaction mechanism. So the global data include ignition delay times, which can be obtained using shock tubes, rapid compression machine, plug flow reactor, and also laminar burning velocities or flame speed, which can be obtained using several types of experiments, such as spherical flames in combustion vessels, Banzan burner, stagnation flow flames, counterflow flames, heat flux burner. So there is a variety of techniques that are available. Ignition experiments are particularly useful for probing initiation and termination reactions and reactions of molecular oxygen with radicals. while they are usually less useful for probing the kinetics of a propagation reaction involving atoms and radicals. So if you remember, yesterday we presented the different classes of reactions. Initiation reactions, which involve the fuel, which can thermally decompose, produce H atom and a radical, or produce two radicals. If it's, for example, ethane, C2H6, you could get CH3 plus CH3, and here you could get C2H5 plus H. The reaction of these radicals with O2 will produce, the reaction of the fuel with O2 will produce the same radical as here and HO2. Propagation reactions are reactions where on the reactant side and product side, you have the same number of active species. So here we have the fuel that reacts with a radical or an atom, produce a radical, and the H atom here is transferred to this radical or atom, and you get HX. So if it were OH reacting with CH3, you would get R plus H2O. There are also possibility of a reaction of a radical with molecular oxygen, giving a smaller species by H atom abstraction, and the formation of HO2. We have also possibility of decomposition of a given radical to produce an olefin and another radical here. And finally, a radical can decompose, forming an olefin and an H atom. For example, C2H5 could decompose and form ethylene, C2H4, and an H atom. And finally, the termination reactions are reactions which involve a recombination of active species, like a radical, for example, an alkyl radical, plus H, giving a molecule of alkane. It can be also two alkyl radicals that recombine to form an alkane. And these processes are the same as those, but the reaction is going on the opposite direction. H atoms are really very important in combustion, and it has been recognized a long time ago already, for example, in this paper in 1947. Burning velocity experiments are very valuable for probing reactions involving H atoms, such as this decomposition reaction, and also a decomposition of a radical forming H atom. Burning velocities are also very sensitive to the main branching reaction in combustion, which is H plus O2 giving OH plus O. And you can see on this plot here, it's a kind of sensitivity analysis where they divided every rate constant in the mechanism by a factor of 5, and then they plot the flame speed obtained originally divided by the flame speed obtained after they reduced the rate constant. And you can see that the most sensitive reaction is that fraction H plus O2 giving OH plus O. This is because it's a branching reaction. You had initially only one atom, and you produce one atom plus one radical. Therefore, by producing these two guys here, you have new channels open. The OH can react with the fuel, and O atoms can also react with the fuel. So as I said before, detailed data are mostly concentration profiles of stable and unstable chemical species that are observed during the oxidation and combustion of fuels. For that, many reactors in combination with sampling method, analytical techniques have been used to acquire such data. Analytical techniques are often used after gas sampling performed using a range of probe, low pressure probe, cooled probe, molecule beam. Or also we can use traps, cold traps, bubblers, trap containing absorbent. So there is a large variety of options here. These probes should stop chemical reactions and transfer a chemical sample to appropriate analyzers without changing its composition. These assumptions need to be verified anyway. So low pressure probes reduce reaction rates by lowering molecular concentration and temperature after gas expansion. So we've seen yesterday that the rate constant, that the rate is proportional to the rate constant multiplied by the concentration of the reactants. So the molecular concentration of reactants will decline, will be reduced when you reduce the pressure. Therefore, the reaction will slow down. And same thing, we've seen that many reactions are pressure dependent and their rate constant increase with temperature. This is not always the case, as we will see later, but for these reactions who are positively temperature dependent, then there is also an effect of on the rate of the reaction. It will reduce the rate of reaction if we reduce the temperature. Cooled probe reduce reaction rates. If they are exponentially temperature dependent, according to the Arrhenius equations that I showed you yesterday. And probes are responsible for disturbance of the reaction medium, flow and temperature, which can result in some complications when we try to interpret the results through chemical kinetic modeling. And I will develop on that a bit later. Many cool traps can be used to collect the condensable compounds at the temperature of the trap. So you can use water ice, 0 Celsius. You can use dry ice. You can use liquid nitrogen. But if you want to use, and there are other mixtures in, if you go to practical chemistry books, you will see a long list of possibilities. If you are using liquid nitrogen traps, you have to be very careful because then you will be able to trap oxygen. And liquid oxygen, which will be stored in the trap, can be dangerous. It can react with hydrocarbons and produce very fast oxidation. Nowadays, the most popular experimental techniques used for collecting such data are flow reactors, such as jet-stirred reactors, tubular flow reactors, but also burner stabilized laminar flames, premixed usually at low pressure. But there are also opposed flow diffusion flames which can be used. And finally, shock tubes and rapid combustion machine to some extent. These techniques by themselves are useful because they cover a wide range of conditions in terms of temperature, pressure, equivalence ratio, initial concentration, residence time, recirculation rate. So temperature, again, is a very important factor because combustion can start around 500 Kelvin and the maximum temperature can be way above 2000. The pressure in practical system pressure can be from atmospheric to several bars or even hundreds of bars. Equivalence ratio, well, especially if you have a turbulent flame, equivalence ratio can go from almost 0 to infinity. And in some pockets, in some regions of the flame. Initial concentration, it varies also a lot because you can have, as I mentioned yesterday, you can have exhaust gas recirculation, which will dilute the reactant entering an engine. Residence time, well, again, residence time can vary a lot if you consider a marine engine and if you consider a sport car. Of course, the residence time in the engine will be very different. And recirculation rate, this is a parameter that is important. If you consider a plug flow reactor compared to a jet stirred reactor, in the plug flow reactor, theoretically the mixture is moving steadily along the reactor, but in a jet stirred reactor or a mechanically stirred reactor, then you have very high recirculation. So then you have more interactions between radical and atoms with the fresh fuel. So the chemistry will not be exactly the same. So through the coupling to large analytical techniques, we can acquire the data needed to validate chemical kinetic reaction mechanism. So among the analytical techniques, some are very popular, where others are less frequently used. Gas chromatography with different detectors, such as conductivity detector, flame ionization detector, mass spectrometry are very popular. Molecular beam mass spectrometry also is used, especially with flames. Fourier transform infrared spectrometry is also very popular, but especially with reactors. These techniques are commercially available, reliable, relatively easy to use, and not very expensive. Other spectroscopic techniques are also used in laboratory experiments. They are mostly used to measure radicals, atoms, and unstable molecular species in the UV or in the infrared, for example. Recent coupling of synchrotron source photoionization with mass spectrometry allowed very detailed probing of oxidation and combustion processes. Several mass spectrometry techniques are used in laboratory experiments. They may differ by the use of different type of mass separation, time of flight, quadrupole, ion trap, orbitrap, and others. and ionization mode, which can be electronic by sending electrons to the molecules that enter the mass spec. It can be a chemical ionization, can be a photonic ionization. It can be also a radioactive ionization. I'm sorry, ionization. By combining the above-mentioned laboratory experiment, one can cover a very broad range of conditions relevant to practical applications, such as internal combustion engine or piston engine, let's say, or gas turbine. This is an overview of the conditions in which we can operate these different techniques. Well, some of these areas have been expanded very recently, but these are the most frequent regime. So here we have the pressure ranging from 1 to 100 bar, and the temperature ranging from room temperature to almost, I think it's 1800. Here we have the plug flow reactor area, which extend from 1 atmosphere to about 100. And the maximum temperature is around 1300 Kelvin in the lower pressure range, whereas at higher pressure, they stop around 1000 K or 900 Kelvin. Rapid combustion machine can operate at relatively high pressure, and most of the time they are limited to about 1100 Kelvin, but they are very useful for probing the low temperature chemistry, the cool phase. Jet stirred reactor, they can operate up to 40, even more. There is one Princeton University which can operate at much higher pressure. They started to do that recently. And the temperature range is roughly between, let's say 500 Kelvin, because there is not much of reactivity below that, but we could operate it at room temperature. Up to about 1500 Kelvin. And shock tubes are covering a very wide range of pressure and also temperature. It can go even way above 2000 Kelvin. But most of the time they don't cover the low temperature chemistry. And finally, engines cover this area here. So you can see that by combining the different techniques, we are able to cover most of the engine operating conditions. This was really what I wrote here. By combining shock tubes, rapid combustion machine experiments, one can probe fuel ignition under internal combustion engine conditions. The measurements of burning velocity and flame structure are limited to about 10 bar. Reactor experiments have limited operating conditions, but by combining them, one can provide detailed data over almost the entire range of pressure and temperature pertinent to piston engine and gas turbine. So now we will have, maybe I can have a look at the questions first. Okay, so the first question is, what does M means in the chemical reactions? Well, it is Na collider. And so if we are working in very dilute condition, it will be the best gas, for example, argon or nitrogen. There are also people who are working under dilute condition with helium, so then it will be helium. Second question, could you explain the difference between Banzan and Mckenna? Yeah. Well, this is quite different because the benzene flame is well, it's just a tube where you premix the fuel and air, and you form a conical flame. I will show that a bit later. You get a conical flame. In the Mckenna burner, you have a porous metallic porous surface, and you are able to stabilize the flame above the burner, and you get a nice flat flame. And there are other configurations where there is a jet flame in the middle. But for Mckenna, this is it. All these techniques intrusive, and which technique can be considered as non-intrusive apart from laser and chemiluminescence technique? Well, as far as you are using a probe, you are perturbating the system. Well, again, this will be presented a bit later today. If you can imagine that if you have a very tiny flame, flat flame on the surface of just above the surface of the burner, and you bring these huge cone for sampling, so then you would have, let me try to draw something. Then you would have this thin flame above the burner, and here you will bring a huge probe. Then, of course, you will cool a region around the probe, and you will also perturbate the flow. So this is one configuration which is a bit annoying. I hope I answered your question. Our ignition delay can be calculated using a rapid combustion machine. I will have a presentation on that a bit later, and also for shock tube. Can we combine the different model to simulate the propagation front flame in close SI? I don't know what SI means. Spark ignition vessel. Well, if you are speaking of a spherical flame which is produced in a vessel after spark ignition, yes, we can simulate these flames. For example, using a Chemkin package. And this is what people are doing when they are using data from the literatures obtained with these spherical, sometimes they call it spherical bombs. All right, so I will continue. So shock tubes and rapid combustion machines. These are what we call in chemical engineering, we call them batch reactor. They can provide both global and detailed combustion data, such as ignition delay times, but also speciation. Why do we call them batch reactors? It's because you will fill the volume where the reacting mixture sits, before you ignite it. And then you repeat the experiments. So compared to a flow reactor where reactants are flowing continuously, here where you can change the initial conditions. Here you will start a new experiment to do that, to change the conditions. It's different. These techniques have been used for several decades. In 1890, Vieille, who was a French scientist, started using compression-driven shock tubes. It was published in the Compte Rendu de l'Académie des Sciences. In 1906, Falk used a rapid combustion machine to determine ignition temperatures. It was published in JAX. So major improvements have been made over the years, allowing the acquisition of very useful global and detailed data for kinetic modelers. And you could have a look at these papers, these review papers, one from Stanford University, in Progress in Energy and Combustion Science, published in 2014. More recently, Sung and Curran published also, oh, there must be a mistake here. I don't think it's the same here. Published a review also in Progress in Energy and Combustion Science. And Goldsboro and co-workers also published a review on rapid combustion machine in 2017. So if you are interested by these techniques, you will find lots of details, and it's a critical review. So they also explain what are the limitations of these techniques, the advantage and limitations. Ignition data from rapid combustion machine and shock tubes can be measured. Rapid combustion machine, as you saw in the previous plot, are limited to the investigation of relatively long ignition delay times and moderate temperature, maximum around 1000 Kelvin, and pressure below 100 bar, roughly. Shock tubes can operate over much wider range of pressure. There are shock tubes, some of them maybe are not used anymore, but which could go way above 200 bars. And they can also be used to probe chemistry at very high temperature, up to several thousands of Kelvin. And under these conditions, the ignition delays are very short. So this is a schematic of a shock tube. So you have two sections here. The driver section, the driver section where you put the gas that will act as a piston, and the driven section where you put your mixture that you want to ignite. And so you have these two chambers, and you have a diaphragm that separates them. Once you have a high pressure, here it's low pressure. And when you break the diaphragm, the piston gas will move in this direction, compress gases, produce a shock wave, which will reflect at the end of the shock tube here and gets back. And this is what is presented here. So you have an incident shock wave, which produces a first increase in temperature, and then you have the reflected shock waves that comes and increase again the temperature. And you have here the signal of a species which is emitting light, for example, and you will have you see that between the time at which the reflected shock wave gets back here and the time at which you start to see a signal, there is a gap, and this is the ignition delay, the time between the arrival of the reflected shock wave and the formation of species, and which results, for example, in emissions. So these are examples of pressure traces, but also a signal of CH radicals. And so these were presented in 1993 by a German group who had a big shock tube, and they were among the first, if not the first, to operate with real fuel-air mixtures. But here you see the kind of signal you observe, and you have this little jump here of pressure, which corresponds to the reflected shock waves, and then the delay until you get a signal. And depending on the conditions, you see that the quality of the signal is not always the same. So this is the way they can determine the ignition delay. And on these two plots here, and also this one, you can see that there is a small increase of pressure in this region, which corresponds to the first stage ignition, in fact, the cool flame. And then there is a second increase of pressure, which corresponds to the hot ignition. And you have the same phenomenon here. And then after running several experiments, you can produce this kind of plot. So here it's a combination of data coming from shock tube and rapid combustion machine. These can be simulated. And well, this is an example where they simulated the ignition of a natural gas air mixture so in a range of pressure up to 20 atmospheres. So the combination of the data from shock tube, which start here around 1100 Kelvin, they extend the range, which is reachable using a rapid combustion machine at lower temperatures. So this type of data are very useful. Nevertheless, when you are modeling these experiments, you must be aware of a complication when trying to combine ignition data obtained in a shock tube and a rapid combustion machine. First of all, they can look irreconcilable. I mean that there can be a big difference here in terms of ignition delay, and you cannot draw a straight line, or even you can hardly draw a continuous line. Sometimes, not on this figure. At first, so they can look irreconcilable, but in fact, it's necessary to consider facility-dependent efforts before combining ignition delay times measured in shock tube and rapid combustion machine. This has been described with great details in the literature, and again, you can refer to this paper by Sung and Kuran. Where they explain how to proceed when you want to use this data. Up to now, a large set of data is available for the ignition of fuels ranging from hydrogen to practical fuels such as jet fuels, diesel, even biodiesel. These data have been extensively used to propose detailed and simple kinetic models. But I think that we must be cautious. There has been models published to properly reproduce ignition delays measured in a rapid combustion machine, and to do so, the modelers had to increase the reactivity. I cannot show you here because it's with methane, but if we were in this region here, the cool flame region, so there would be so high temperature and then something like this. And so here we are, this is the cool flame and the negative temperature coefficient here. And then we are in the high temperature regime. And it's rotated. So the models initially were around here, and then it was okay. But here there was a gap, and they tried to reduce this gap, and I'm not fully sure that it's always reasonable, because previous models were able to simulate properly results obtained in laboratory reactors where conditions are well controlled. But once you want to fit the rapid combustion machine data at a very low temperature, then you lose the capability to reproduce laboratory experiments such as jet stream reactor experiments in the low temperature region. And then you have, when you look carefully at what is predicted in terms of temperature and, for example, the concentration of the fuel. So the experiments will be like this, and the modeling will be like this in this region, and then maybe shifted, something like that. And my understanding is that it's due to the fact that they pushed the model to fit this data. And then I will show you later that nowadays we are able to probe some of the low temperature intermediates, such as ketohydroperoxide, and you will get something like this, but the model will predict something like this. A difference of temperature which can be, well, up to 100 Kelvin, and there is no reason for that. Before so yes, we need to be careful when we use this data, and it's easier when you are both experimentalist and modeler. Then you know what are the potential problems with your own data, and maybe you will not try to push things too far. I will stop here because then I will start to describe speciation, which is a different topic. Let me have a look at the questions. Could surrogate validation for ignition delay be in ignition quality tester before being validated in engines, since no validation data available for the target fuel in shop tube or rapid combustion machine? Well, this is a very difficult question. I will never try to use ignition quality tester or to produce something which will be used in chemical kinetics. But this is a nice device that gives you a flavor of what of how the engine would respond, yeah, it's useful, but for me, certainly not for chemical kinetics. Another question before we have the short break. No? So we get back at in 10 minutes. All right, so we are back, and what we will describe now is species measurements from shock tubes and rapid combustion machine. Speciation in shock tubes has received much attention. Studies concern both oxidation and pyrolysis. More limited database is available from rapid combustion machines. And currently there is at least one machine in the US where they do measurements, species measurements. One in France, and I think it's about it. Several research groups have used shock tubes to measure species concentrations using spectroscopy. And particularly the group of Professor Hansen at Stanford University, and also at DLR and Duisburg University in Germany. Gas chromatography was also used. There is a paper in the Review of Scientific Instrument from Rob Tranter, which describes that, another one by the same authors in PCCP. Anson and co-workers have recently reported the laser absorption-based measurement in shock tubes of time history of reactants, small radical, some stable intermediates, and combustion products. And on this slide, you can see an example of the kind of results they can get. So the dashed line represents the chemical kinetic modeling, and the continuous line represents the data. And you can see that under this particular condition, for the oxidation of ethylene, there is a very good match between the data and the modeling. So this kind of detailed information is very useful to probe the validity of a chemical kinetic model. So here the temperature is pretty high, and you see that the I'm sorry, I said ethylene. It's an experiment with normal heptane, 300 ppm of normal heptane. So we are very far from a mixture of fuel and air at F=1. It's very, very diluted in order to produce this kind of very nice measurements. You need to work under very dilute conditions. So the beauty here is that you probe both products, final products, CO2, water, intermediate, and a radical, OH, which is one of the most important species to drive the reactivity of the reacting nature. This is another example of measurements from the group of Professor Brzezinski. So here they operate at very high pressure, and these concentration profiles are obtained by sampling the toluene oxidation in their shock tube. So here they use a single shock tube, and they have a gas sampling system with GC analysis, which can provide this kind of data. So the fuel is here, and they probe the formation of CO here, and they have two types of initial conditions. That's the reason why you have open and closed symbols, and the modeling is represented by lines. So again, you can see that there was a very good agreement between the data and the shock tube, and the shock tube data and the modeling into these conditions. More recently, the technique has evolved, and there are some miniature high repetition rate shock tubes that appeared. So it was introduced by Tranter and co-workers and Lynch, and they published first paper in the Review of Scientific Instruments in 2013. So initially they used it to probe the pyrolysis of dimethyl ether at high temperature, between 1400 and 1700 Kelvin, and relatively high pressure. And they ran these experiments at the Advanced Light Source in Berkeley. And they use a tunable synchronous generated photoionization time of flight mass spectrometry to do that. This new setup clearly opens new horizons for chemical kinetics. Because using this very sophisticated technique, they can probe the formation of intermediates. They can follow the concentration of radicals, and this is extremely useful when you want to calibrate your chemical kinetic reaction mechanism. Data obtained in shock tubes have been extensively used to propose detailed and simple kinetic models for the oxidation of fuels ranging from hydrogen to large hydrocarbon, and even commercial fuels such as gasoline, jet fuels. And you can, if you are interested, you can refer to these different papers or publications. This is a this is a PhD thesis. Species measurements in rapid combustion machine is performed through gas sampling, and it started in the 60s. Several groups have performed such experiments for the ignition of hydrocarbons, alkene nitrates, oxygenated fuels. GC has been used extensively in most of these rapid combustion machine experiments, but they also used exhaust gas analyzers to probe the concentration of CO, CO2, NOx, and unburnt hydrocarbons. So there is a relatively large set of data in the literature. And more recently, Margaret Woolridge, Michigan University, also developed a rapid combustion machine where they take samples and get concentration profiles according to operating conditions. Spectroscopic methods in the UV and infrared have been used, and started with studies of fish and coworkers in the 60s. These data have been used to propose detailed and simple kinetic models for the oxidation of fuels from hydrogen to oxygenate and large hydrocarbon. And again, you can, for details, you can refer to this Progress in Energy and Combustion Science paper by Song and Kiran. But these experiments also serve to identify the products of low temperature oxidation of a range of fuels. And this was done at the University of Lille by Minity and coworkers, and in Michigan University, in the group of Margaret Woolridge. So the advantages are that we can run with very little fuel compared to flame and reactor experiments. Wide range of operating conditions in terms of pressure, temperature, equivalence ratio is covered by combining these techniques. What are the limitations and weaknesses? Well, batch reactor experiments are time consuming because you need to feed the reactor, then you run the experiment, then you clean the reactor, you fill the experiment with the reactor, and you start again and again. And so this is time consuming because it involves the mixture preparation, pumping after each experiments, replacement with your shock tube, replacement of the shock tube diaphragm. And most of the cases, it needs disassembling or reassembling. Also, pressure history must be well characterized to allow accurate kinetic modeling. And this is a specific point which has been addressed in recent literature. Now we have also the possibility to use flow reactors. So then it's not a batch reactor. You are flowing continuously the reactants through the reactor. It can be a tube or it can be a stirred reactor. So flow reactors are particularly useful for measuring the concentration of reactants, intermediate species, and final products of fuel oxidation or pyrolysis, or interaction of fuels with other species, for example, NOx, SOx, dilution by CO2, by water. Nowadays, people are also interested in the interaction with ammonia. We usually operate at temperatures below 1500 Kelvin and pressures of less than 50 bar, although there are some experiments that, very few experiments that can go above that. The limitation to 1500 Kelvin is related to the use of fused silica in many cases. Then above that temperature, it gets fragile, and people usually do not go much further than 1500 Kelvin. They are particularly useful for studying the low temperature oxidation chemistry of fuels and intermediate temperature oxidation also. In most of the experiments, high fuel dilution is used, which means that you are in the range of 100 to few thousand ppm. To do so, you can, by doing so, you can avoid flame to occur in the system, and also large temperature gradients. Nevertheless, experiments are also performed with higher initial fuel concentration, let's say 1 to few %. Well, this is useful if you are interested in probing some unstable intermediates that are formed at very low concentration. Then, if you want to see them, you need to increase the concentration of the reactants. Otherwise, you will probably miss them. But by doing so, you are you can you can operate under conditions where temperature gradients are larger, and then when you want to use the data for chemical kinetic modeling, they are less accurate, most likely. So as I said before, for shock tube experiments, it's better for the kinetics to operate in very dilute conditions. Well, in tubular flow reactors, ideally called plug flow reactors, one can observe a chemical reaction along the main axis of the reactor. In jet stirred reactor, the chemical composition is ideally homogeneous, which means that wherever you probe inside the reactor, you should get the same answer. Flow reactors are usually heated by external ovens, and temperature measurements are of great importance for running accurate modeling. So you need to measure the temperature inside the reactor and report it for the kinetic modeling. In tubular reactor, this means that measurement must be made along the reactor axis. In jet stirred reactor, temperature homogeneity is usually verified along the main axis, and measurements used as input in isothermal perfectly stirred reactor model. Compared to flame experiments, flow reactors are not limited to flammability limits, which means that you can operate almost from 0 to infinity in terms of equivalence ratio, from the extremely lean conditions to pyrolysis. And this is similar to what we said before for shock tubes. Although this is not very common, tubular flow reactor operating under plug flow conditions can be used to obtain emission delays, and I will show you an example later. So species measurements, two types of flow reactor are mainly used in recent kinetic study. Tubular flow reactors, which consist of a tube where reactants are injected and heated from the outside. The flow inside the tube can be laminar, and this is the case for many reactors, or turbulent. And this is mostly the case for the Princeton reactor that was operated in the group of Fred Dreyer. And this is another reactor that I show you. An Australian reactor presented in measurement science and technology pretty recently. This reactor can operate up to 50 bar. It consists of a quartz tube here. Well, they probe from the top and send the samples to different gas sampling, an Orba bench that I mentioned earlier, online gas analyzer, and also they can store their sample and analyze them by GC, different type of detectors. And this is one of the turbulent flow reactor that was used in Princeton. So this one was horizontal. They had also one vertical, and they were also probing the reacting mixture and sending them to different analyzer, including GC and FTIR. Molecular beam mass spectrometry and tunable synchrotron vacuum UV photoionization have been introduced recently. And in this paper, they report some data. And this is, as before, as mentioned before, with the micro shock tubes, it's opening new horizons for the understanding and validation of chemical kinetic reaction mechanism. This technique allow to probe some of the intermediates that couldn't be probed using standard or more conventional techniques. So on this slide, I show the reactor that we are using in my group. Several jet-stirred reactors with different geometries have been used. Some are spherical, like this one, hemispherical, toroidal, near conical. But the most popular design is a spherical reactor of about less than 50 cc. This technique potentially allows operation over a wide range of residence time, from a few milliseconds to several seconds, depending on the reactor geometry. And you can, if you are interested, you can refer to this paper published in the Canadian Journal of Chemical Engineering, where they present the rules they designed at that time to build perfectly stirred reactor. Temperature homogeneity is very important, and it can be improved through preheating. We preheat the reactants before they enter the reactor at a temperature close to the reactor operating temperature. And this is what we've been doing for a while. Composition homogeneity was shown in previous work to be relatively easy to achieve, and this can be verified by probing along the axis of the reactor. This is the reason why we are using this pyramidal configuration, which allows you to move a thermocouple to the top of the reactor. So this reactor has 4 injectors and with opposite direction of the jets, one to the other. So this one goes down, this one goes up, this one goes to the left, and this, the guy behind goes to the right. This is a different design from MIT. Toroidal jet stirred reactor built with alumina. And here we don't have 4 injectors, but we have 32. So all around the Tor. And it was used in different studies, and it was even coupled with a plug flow reactor. And I think I have one slide later. So this one is a single jet stirred reactor. So the reactor itself is here. Okay, you can see it here. And you are sending the reactants. They are impinging the surface here and going back. And there is some steering which occurs. Of course, it's not as perfect. The homogeneity inside is not as perfect as it could be in other designs. And this one was used for some time in Seattle, the University of Washington in Phil Maltese group. And the data were used very early by Lawrence Livermore to propose some kinetic reaction mechanism. So these reactors have been used to provide useful data for modeling the pyrolysis and oxidation of a wide range of fuel. And so from hydrogen to diesel, including ammonia, carbon monoxide, syngas, wide range of hydrocarbons, saturated, unsaturated, cyclic, aromatics, oxygenates, complex fuels such as gasoline, jet fuel, diesel fuel, synthetic jet fuels, or synthetic diesel fuel, and biodiesel. As I mentioned before, the experiments also were performed to probe the interaction between the oxidation of hydrocarbons or hydrogen or syngas with traces of NOx or SOx also. The interaction of ammonia with NOx, you know that in order to reduce the emission of NOx, we can inject ammonia. And this process has been studied in such reactors also. So I will show you some examples of experimental results obtained using this type of reactor, and we compare data obtained with conventional Jet A1 and 2 synthetic jet fuels. And here you have Jet A1, the black symbols of Jet A1 data. The open symbols, let me see. Yeah. So here we have the GTL, which are the open symbols, and on the on the right-hand side, the close symbols are CTL, cold to liquid, and the GTL are open symbols still. So we operate the reactor at 10 bar under stoichiometric condition with a residence time of 1 second. And we observe the consumption of molecular oxygen here, and the formation of different intermediate or products, so the formation of CO here. And you can see that the profiles are very similar. The formation of water, again, very similar, and that of CO2. And here it's the formation of hydrogen and the intermediate formation of isobutylene. And for regarding the comparison between GTL and CTL, you can see that under the cool flame regime here, there are differences in terms of reactivity. And besides that, the consumption of oxygen is relatively close, as well as the formation of hydrogen. So it shows that most likely the behavior of these three fuels under similar conditions is similar. Although there are some differences, and if you look in details at the formation of, for example, isobutylene, you see that there is more isobutylene formed with the CTL than with the GTL, and this is directly related to the composition of the fuel. Well, while gas chromatography and FTIR spectrometry are usually used in conjunction with small sonic probes in jet stirred reactor to probe the chemistry, molecular beam mass spectrometry and tunable synchrotron vacuum UV photoionization have been introduced recently, and it started in 2011. About 10 years ago. And this allowed to have more detailed investigation of the combustion chemistry of the oxidation processes which occur. And even more recently, some results have been obtained through the combination of jet stirred reactor with very high resolution mass spectrometry and using different ionization mode like chemical ionization, but also electrospray. And they demonstrate that currently accepted reaction scheme for simple hydrocarbons, oxidation or missing reaction pathway, which lead to the formation of highly oxygenated molecule. And the inclusion of such products and reactions in the scheme could significantly change model production. So these are an example of the type of chemicals that we have been looking at using different experimental setups. So this one's a jet stirred reactor with photoionization molecular beam mass spectrometry. these are experiments performed at Berkeley National Lab at the Advanced Dye Source. These are experiments of the same type, performed at different temperature. And here, these are experiments performed in a jet stirred reactor coupled to high resolution MS system, an orbitrap with chemical ionization. And here, the experiments were performed after an engine, a CFR engine, and the analysis was done by chemical ionization and orbital measurements. And you can see that from this figure, you can see that most of these oxygenate molecules here that we could probe are similar whatever the system. And this is the system that we use right now in my group. So we use, so we have a jet stirred reactor, which is located inside a pressure resistant housing here. We have here the heating wires around the reactor. So we feed the reactor with the fuel diluted by nitrogen, which is sent to a capillary that goes up to just before the entrance of the reactor. And in parallel, we send a mixture of nitrogen and oxygen. These two flows reach the mixing point here, and then they go through the injectors and enter the reactor. They react, and from the bottom we can move a sonic probe, which will probe the reacting mixture, and this sample will bubble in acetonitrine, cooled acetonitrine for a while. And then we will use this solution either by direct injection in the electrospray or APCI source, or we will inject it in a liquid chromatographer. And so the sample enters this ionization chamber. We get ions which are separated and detected in this orbitrap here. And then with this technique, we are able to probe some of these intermediates we are interested in, such as keto hydroperoxides or more oxygenated products. And so these are examples of results obtained during the oxidation of dipropyl ether. And so this is the kind of keto hydroperoxide that we can see, and this is a nice mass spec signal. And what we did also is to make sure that we have this hydroperoxy function here. We use the HD exchange using D-tool, and then we looked for the ions corresponding to this exchange, and we could see the ions corresponding, which confirm that there is an OH group here. And we did this same experiments probing highly oxygenated molecules. And in the case of dipropyl ether, we could probe species having up to 8 oxygen atoms. We tried also to figure out what was the structure of these different keto hydroperoxide. And to do that, we use liquid chromatography and try to separate them Well, these are initial data. We've been to do better later on. And this work was presented at the last Combustion Symposium. So we separated the different isomers and then proceed to fragmentation of these ions here. And based on the fragmentation, we could figure out which were the structures, which was the most important isomers which are formed during the oxidation of this fuel. So typically, this kind of experiment was probably not possible 10 years ago because these instruments were not available to people. Other techniques have been used to probe unstable species or difficult to measure species. So quantitative measurements using cavity ring down spectroscopy in the near infrared was used to probe the formation of HO2 and also H2O2. And we did that in a jet stirred reactor at atmospheric pressure. So we suck a sample from the reactor and send it to this cavity ring down spectrometer, and can collect a signal that we report here as a function of temperature. And these data are compared to different chemical kinetic mechanisms which were available at that time in the literature. So you can see the formation here of HO2, which peaks around 600 Kelvin. And some of the, well, one of the kinetic model represents fairly well the data. This type of data is useful to further probe the validity of reaction mechanism. The problem with this type of chemicals, but also this type of chemical, is that there is sometimes there is large uncertainty. Here we cannot produce standards. So far we haven't been able to get quantitative measurements. We have only qualitative measurements. And here, well, error bars are still large, and it's difficult to reduce them. But it's always the case when you are dealing with unstable species, because they can decompose during the sampling. And well, it's a difficulty that is difficult to address. Yeah, as I mentioned before, jet stirred reactor and plug flow reactor have been combined at MIT in the 90s. To allow probing the combustion chemistry over a wider range of residence time, because they were using this toroidal reactor here, which operates at very short residence time, and at the exit of the reactor, gases were flowing through a plug flow reactor. Then they could increase the residence time quite a bit. This original design was later modified at NIST by Leonard and Manzello. And I think they use it to probe the formation of polyaromatic and soot. All these reactors can be pressurized. And so this is the reactor presented by Rasmussen and co-workers is one which is operating at a very high pressure plug flow reactor. And the one that we use here in Orléans can operate up to 40 bars. At that time in 86, it was limited to 10, it can go up to 40. Usually fused silica reactors, which you can call quartz also, fused silica, are commonly used, but there are reactors which are built in different material, like metals. This is the case of the reactor, the gesture reactor developed by Mignola and co-workers in the 80s. It was located in Naples, Italy. But there are other reactors in Belgium, for example, here, which is also made of metal. Refractory materials are also used, like ceramic or aluminum. And so the reactor from Phil Maltese group, used in 1988, is in ceramic, I believe. And also in Spain, they are using these refractory materials. Whereas fused silica is generally considered chemically inert in combustion studies, other materials such as metals have catalytic activity that cannot be ignored. And well, we must be careful when we use the data coming from these different type of material. This is schematic of the reactor used in Ghent in Belgium. And the reactor is made of Inconel, Incolloy 800 HT, which is similar to Inconel. So it's a metallic reactor. It's different stages of heating here. So what are the advantages and disadvantages of these reactors? Well, operating temperature range and the possibility to investigate pyrolysis and oxidation is nice compared to flame, which are limited in terms of equivalence ratio. Reactors are particularly useful for gaining insight into reaction products and intermediates through the use of advanced detection techniques, or even quantification techniques. Numerous analytical techniques are used after gas sampling, achieving gas sampling achieved using a range of probes for stopping chemical reaction and transferring chemical sample to the appropriate analyzers. Nevertheless, one should be aware of the possible complications associated with reaction on the surface of the reactor. And faster the reaction in the gas phase, probably less important or less influential are these reactions. But when the system is running slow, then these reaction, the importance of the reactions can be non-negligible. What are the main disadvantages? Well, can operate over limited temperature, pressure, and residence time. This is due to material range of use and reachable flow rates. As I mentioned before, well, some of these materials, such as fused silica, cannot be used above, let's say, 1500 or 1600 Kelvin. Experiments need much larger fuel quantities compared to shock tube or rapid combustion machine, where you just use some vapors, because it's these are batch reactors. It will depend on the number of experiments you run. Here you are, it's a continuous flow with these reactors. So you are continuously sending the fuel to the reactor. The quantification of intermediate species by photoionization remains limited due to unknown photoionization efficiency, which is particularly difficult to compute using current theoretical methods, especially when you are dealing with large species. Let me answer the different questions that we have here. So, species mode profile in the plot of slide 68 are these sampled before or after ignition. If before, doesn't the ignition raise the temperature and change concentration? So 68. Well, you can see here that the reaction starts above 1240 K. So here ignition as we are within the ignition process, but they are able to accurately identify what's the temperature in these experiments. So there should be no major problem. Second question, this is how rate constant determines spontaneous by analyzing the sample gas. Could you also please advise how frequency factor is estimated for each fraction? Well, I don't know exactly what it refers to, but some of the rate constant which are used in different chemical kinetic models are deriving from experiments, and I will explain how you can measure or determine rate constants. But sometimes they are estimations based on similar reactions for which we have the rate constant. And thirdly, we can also get this type of input from calculations, Rcem calculations, for example. So all these models are for the autoignition system. If you want to use one of them for a spherical container, as mentioned, or cylindrical with spark ignition, which model may be appropriate for the real phenomena? Well, if you want to simulate spark ignition, well, if it's in a spherical device, a spherical bomb, let's say, and you are interested in flame speed, it can be done with several of the available kinetic models in the literature. Then if you want to simulate spark ignition in an engine, it's a different story. Because the deposit of energy is not something simple. It cannot be done right away. The experimental conditions are in no pressure and temperature, 1 bar. Well, okay, but I'm sorry that I have difficulties to follow up in this chat. Well, sorry, I cannot answer this question. I don't understand what it refers to. But you can send me an email and I will try to answer if it's more detailed. Maybe we can have a break now and get back in 10 minutes. Okay, so let's continue. So as mentioned a bit earlier, besides the use of shock tubes and rapid combustion machines, we can use perfectly plug flow reactors to obtain ignition delays, and this is an experiment that was built at the University of Aachen in Germany, where they use this flow reactor here to determine ignition delay. So the first stage, ignition is observed as temperature increase of a few degrees in the reactor. After the first ignition, strong heat loss to the reactor wall reduces the temperature and stops chemical reaction. The first stage ignition is determined based on the distance between the fuel injection and the location of the first temperature rise and the flow rate in the reactor. So this is the setup again with so here injection of air, oxygen, nitrogen, liquid fuel, and so there is a vaporizer where they vaporize the liquid fuel. That is coming from liquid mass flow controllers here, and then there is an heated line that can be used to send the mixture, the reacting mixture to the reactor. And here they are burning what goes out the reactor. And this is the kind of result they could obtain. It was for dibutyl ether air oxidation at 1 atmosphere. And the data are compared to modeling, and it looks like there is a good agreement here for the oxidation of this fuel under relatively low at relatively low temperature between 500 and 700 K, something like that. Flames can be used also to provide data usable in chemical kinetic reaction mechanism. So laminar flames are used to obtain both global, laminar burning velocity, and detailed spatial speciation or flame structure data, which are used to validate kinetic reaction mechanism. Experiments are currently perform over wide range of pressure, typically from 0.04 to 60 bar. And burning velocity have been obtained from about 0.1 to 60 bar, whereas flame structure are available up to about 10 bar. Major improvements of the methods have been made over the years, allowing the acquisition of very valuable data for kinetic modelers over a wide range of conditions and for many fuels. And this is, you can have an overview of what is available in this review paper published in Progress in Energy and Combustion Science in 2012. And also still in Progress in Energy of Energy and Combustion Science in 2014. Laminar burning velocity. The laminar flame speed is defined as the propagation speed of a steady, laminar, one-dimensional, planar, stretch-free, and adiabatic flame. It is an important fundamental property of a flammable mixture, being a measure of its reactivity, diffusivity, and exothermicity. It constitutes an important validation target for chemical kinetic models and a key parameter in turbulent combustion. Burning velocity can be extracted from a range of experimental conditions, and we can, among them, one can cite a soap bubble method, flames in tubes, a flat flame burner method, conical flame or Banzan flame, heat flux burners, spherical flame in constant volume chamber, which we call also bombs, and stagnation flame opposed flow method. So this is an example of a Banzan flame where the flame speed is obtained by the so-called cone-angle method, according to this equation here. So this is certainly not the most sophisticated method, but for some fuels, it is still useful. Spherical flame in a constant volume chamber. Well, this is rather popular nowadays. So these are Shadowgraph that I show here of temporal evolution of fuel air flame front and the pressure of 1 bar and initial temperature of 423 K for an equivalence ratio of 0.9, slightly poor. So we observe here the temporal increase of the flame radius, and this is used to obtain the flame speed. The end stretch burning velocity is obtained after extrapolation to zero stretch using several methods available in the literature. So here you get a spark, ignition, and propagation of the flame. That stays pretty spherical. Nowadays, spherical flames in constant volume chamber and stagnation flame opposed flow method are the most widely used techniques. They have been reviewed recently by Renzi and co-workers and Egolfopoulos and co-workers. These are the same review paper I mentioned a bit earlier. High pressure and temperature conditions are hardly reachable using Banzan flames, counterflow flames, and heat flux burners. Most of the results reported at elevated pressures were obtained with spherical expanding flames. One limitation of this method comes from the fact that the spherical flame surface is changing during propagation, inducing stretch effect, which must be accounted for using extrapolation method. And until 1985, the paper by Wu and Low, and these stretch effect were not well considered, and they led to lots of scatter in measurements. So there has been a significant reduction of uncertainty on flame speed measurement from after the work of Edlow and co-workers on stretch corrections. For methane air flames, for which the plus or minus 25 centimeter per second scatter in the old days got reduced to about 2 centimeters per second more recently, by considering the non-linear nature of stretch on burning velocity. With such low uncertainties, burning velocities are very important and valuable data for kinetic models assessment. The other technique that is presented here is a twin stagnation flame, where you send fuel and oxidizer on both sides of the burner, and you will get these nice flames here with quite a large section which is flat. And so this is another technique that can be used. And burning velocity, I mentioned before, have been obtained for fuel as simple as hydrogen, but also for a practical fuel. And this is an example of results obtained for the combustion of synthetic jet fuels. And jet fuel. So jet A1, we have these measurements here. We have also real GTL, GTL surrogate for the simulation, and GTL surrogate for the experiments. And all the data obtained with a different GTL sample. And you can see that there is this bell-shaped behavior that is usual for hydrocarbons. These were obtained at atmospheric pressure, initial temperature of 473 Kelvin. And these experiments were simulated using a detailed kinetic reaction mechanism, which fit very well the body of data that are presented on this graph. Species measurements in flame, that goes back to 1947. Nowadays, flame structures mostly come from two methods: low pressure premix flat flames and stagnation flames. These techniques have been reviewed recently by Golfopoulos and co-workers in Peck's paper that I mentioned already, 2014. So in these experiments, samples are extracted from the flame using a probe and sent to analyzers like gas chromatographs and mass spectrometers. Molecular beam mass spectrometry has been used extensively, and more recently, photoionization by a synchrotron-sourced vacuum ultraviolet radiation was employed, generating a large body of kinetic data unreachable by other techniques before. And this is reviewed in this PEX paper, and there are different key papers related to this. This one review of a scientific instrument in 2006, for example. Of course, we can use other techniques, optical measurements, to probe what's going on in the flame. Here it's a schematic of the experimental setup that is used at Berkeley National Lab. So this is a low pressure Mckenna burner. Gases from the flame are sampled through a fused silica probe. And you can see the probe here. And this probe has two angles. This first angle, and then another one, wider. And the sample goes to a time of flight mass spectrometer, and ionization occurs by photons coming from a synchrotron. And so using this technique, they've been able to measure stable and unstable species. There are many papers in the literature reporting data. Fused silica probe can cause significant perturbations to the flame, making it difficult to model and interpret the experiment. And this is especially the case close to the burner. And this was demonstrated by Niels Hansen and co-workers in a commercial and flame paper in 2017. Also, the use of a thermocouple, so the effect here is flow perturbation plus thermal perturbation, cooling. Also, the use of a thermocouple for measuring temperature profile in the flame can alter the flow field and temperature profile. And this has been described in several papers in the literature. Although these effects are small compared, well, generally small compared to sampling probe perturbation. Nevertheless, a wide range of fuels have been studied in flames, and examples of concentration profiles measured in low pressure premix flames of toluene are presented in the next slide. This is what I wanted to show you. So you can see here they vary the equivalence ratio from fuel lean 0.75 to fuel rich 1.75, and they probe a range of species. So the different species they probe are acetylene, propangyl radical, vinylacetylene, cyclopentadienyl radical, benzene, benzyl. They probe also phenylacetylene, ethylbenzene, indenyl radical, indene, naphthalene, and phenolphthalein. And the fuel is toluene. And these experiments were performed by molecular beam mass spectrometry using photoionization from synchrotron light. So you can clearly see here the effect of equivalence ratio on the formation of these intermediate products like acetylene. From the green data here, where there's very little acetylene form under fueling conditions where we have excess of oxygen, we move gradually to much higher concentration. So here it's mole fraction times 10 to the minus 3. And another example is the variation from for C5H5 cyclopentadienyl, and again there is a dramatic increase which is overestimated by the model. Phenylacetylene again from almost zero formation in fueling conditions to high concentration here in fuel rich. Same for indene here. Same for naphthalene. So naphthalene, it's two aromatic rings fused. And we have the same behavior for most of the species that they probe here. Another example is propalgil. Propalgil is very important radical intermediate involved in the formation of aromatics. And the model is in reasonable good agreement with the data. At least in under fuel-rich conditions. So this is the kind of data that can be produced using this technique, flat flame burner at low pressure and coupled to NBMS. And a large variety of fuel can be studied this way. So to go back to the effect of temperature and temperature perturbation by the cone, we looked at data coming from Hofe, where they oxidized. I think it was the oxidation. Yeah, it was the oxidation of ethylene. And in this flame, they could measure the temperature in presence of the cone and without the cone. And we have these two different profiles here. And when we are simulating the flame, depending on the profile, the temperature profile we use, we have a very different prediction of some of the products we were looking at. And especially here, we got interested in the formation of a low temperature product, which is this C2H5OH, hydroperoxyethylene. The experimental data are represented by these dots here. And you can see that close to the burner, we have a formation of these species apparently. And if we run the simulations without taking into account possible perturbation of the flame, we get we don't get this dotted line. We get this dotted line, but 100,000 less important. So it's almost zero. But then if we consider that the temperature here drop by quite a bit, then we are within the experimental error as shown here. So clearly, this perturbation by a probe can have a significant effect on the the formation of low temperature chemistry species. We do not claim that it will have an overall important effect on the other products, but clearly these species, these kind of species could most likely not be formed in the flame without perturbation from the cool. And so to do that, we used a kinetic model which was proposed in the literature for the oxidation of ethane at high pressure and relatively low temperature. So it includes low temperature chemistry. And we ran it and we looked at the different pathways as a function of temperature and the importance of these different reaction pathways as a function of temperature. And you can see here it's 555 K, so it's this temperature. And here it's 755, which is between this data point and this one, it's about here. And you can see that the formation of this this product of low temperature chemistry here is much more important under these conditions than here. Well, this time of flight mass spectrometry with photoionization by synchrotron light are very useful for detecting intermediate species. There is a difficulty. It's the differentiation between isomers. When photoionization energies are too close. And then we can complement these measurements by GCMS measurements. And this is what was introduced by Dias and co-workers in Louvain in Belgium. They used a method consisting of a conventional electron impact MBMS setup, where a portion of the sample is sent to a GCMS through a capillary, which allows the separation of isomers of stable products that could not be differentiated based on their ionization energy or mass. And other workers also combine electron ionization MBMS measurements and GCMS measurements to get better characterization of isomers. And this is I refer to a paper published in the Proceedings of the Combustion Institute in 2017 for those of you who are interested. So we've tried to cover lots of things here a bit briefly, but again, for more details, you can refer to literature, especially papers published in the Progress in Energy Combustion Science are very useful, and you will get lots of details and additional information. On the most common experiments for kinetic mechanism assessment have been presented here. It was shown that shock tube and rapid compression machines are very useful for determining fuel ignition properties, but also to measure chemical products. Recent advances in CFD modeling for rapid compression machine are expected to facilitate the use of rapid compression machine ignition data in kinetic modeling validation. Tubular flow reactors and jet stud reactors are commonly used. They, coupling with advanced analytical techniques, is able to provide unique data for kinetic models assessment. However, There are limitations due to unknown photoionization efficiency for many intermediates, and this must be addressed in the future, maybe through the use of more advanced theoretical methods. Flames can also provide valuable data in terms of burning velocity, especially nowadays with the new data, which are stretch corrected, but also through speciation. Although, as I just mentioned, there are limitations due to perturbation by conventional large sampling probes, and this remains a challenge for the future. I really do believe that there are some progress that can be made in this area in the future, especially by combination of computations and experiments. They should go together. So to summarize, we looked at shock tubes and rapid combustion machines. Shock tubes and Rcem are very useful for determining fuel ignition properties, but also to measure chemical products. So in terms of fuel ignition properties, and also to answer some of the questions I had, of course, there are some instruments nowadays which are available to determine cetane number, derived cetane number. But since they are using injectors which are similar to automotive injectors, probably these are interesting instruments to compare data with engine data, but to perform kinetics, I'm not convinced one can do kinetics with these instruments. But it's very useful, and we've been using this type of instrument to obtain certain numbers of surrogates and real fuel, and adjust the composition of the surrogate in order to get closer to the real fuel, and then use these surrogates in our chemical kinetic model. So to some extent, it can be a useful instrument, but I don't believe we can really do kinetics with this. There has been some efforts in this area by Tony Dean at Colorado State of Mind. They published several papers where they investigate the possibility to use these instruments for kinetics. Flow reactors, tubular flow reactors, and stirred reactors are commonly used. We've seen that there are different designs. They can be coupled with classical analyzers like GC, GCMS, FTIR, and other analyzers. For example, these exhaust gas analyzers. But also they can be coupled to advanced analytical techniques, which are then able to provide really unique data for kinetic model assessment, and also to indicate that there are some pathways that must occur because we are able to detect species we were not expecting. And I will elaborate a bit further later on this. So these are very interesting techniques, and there is still lots to do with these techniques. And finally, flames, they provide valuable data in terms of burning velocity and speciation. But be careful with the interpretation of some of the data. There can be some difficulties due to perturbation by probes, especially when you are using large probes. And what I didn't present here are all the optical techniques that can be used in these different systems. So they can be used in shock tubes, of course. Well, I did present a bit of the data obtained at Stanford, for example, but not much more than that. And but rapid combustion machines can be also equipped with optical system. Same for flow reactors and of course for flames, where you can use different techniques. For example, LIF, laser-induced fluorescence, but all the techniques are available also for that. And I think I will close here. I would like to spend more time answering questions. I see I have 2 questions here, but I am ready to carry on forward. Okay, so can the laminar flame velocity be calculated in RCEM using Shadowgraph method? Yes. How can one remove the effect of flame stretching? Well, there are different methods which are described in the literature, where you extrapolate the 2 conditions where stretch is 0. There are linear and non-linear methods. Well, I cannot go into this type of detail, but if you look at the Progress in Energy and Combustion Science, a paper by Egolfopoulos and co-workers, there are informations, and also they give you a reference to some original papers where it is described. In premixed flame produced by a Bunsen type burner, which temperature measurement techniques provides the most accurate value for temperature measurements? Well, probably the best technique is optical, and it can be done through LIF. Can you please comment on the use of heated constant volume combustion chambers to study fuel ignition properties and products of combustion? Well, constant volume combustion chambers, for me, they are only used to measure flame speed. If we are speaking about the same device, that's all what I can tell about this. Any other question? Well, again, well, I'm not sure I understand this question. Please send me an email. I will answer directly to you, Dennis Bunting, and I will try to answer as precisely as possible. through this kind of chat, it's not so easy to interact, at least for me. All right, so if there is no more question right now, we can close the session. And oh, yeah, well, you, all right. My email, yes, well, okay. So Anthony M. Dean is the right person, yes. I cannot remember the name of his student who worked on this, but yeah, this is the right person. And they started to work on this problem less than 10 years ago, I would say. Yeah, you can have my my email, Salim. You can have my email. I don't know how to. I will type it. No more questions before we close? Okay, so good afternoon and see you tomorrow morning.